Terrific. Thank you so much, and hopefully you can hear me. The important thing is that I am actually on time as scheduled because you've got to get the bad presentation out of the way first. That was made very crystal clear to me. So today we're going to talk about low carbon concrete, the demands of the owners, and ask the question, are they realistic? You know, it's like anything else, and I see that like a classroom, the classroom fills up from the back. This room is filled up from the back, and so the question becomes, you know, do we get always what the owner anticipated? And you know, concrete construction is an interesting thing, right? Because we can fix a lot of problems in the field. This is why I no longer run my contracting business, right? Because they make the windows the wrong shape. So, and we live in a pretty simple world. And the simple world that we live in is based on specifications. And so a specification is part of the contract documents. It comes together and it clearly tells us as the contractor and communicates from the designer to the installer exactly what all of the requirements for the construction are. We then ask for a submittal. The main purpose of the submittal is to make sure that the contractor has read the specification and has responded to it. It also gives us something to do in a couple of weeks, which is always good. And then a testing lab is hired to check, to make sure that what is being provided to the site is in fact what was in the submittal. And there are no problems, and so everything is great, and I will talk to you next year, right?
Works
so
just like that.
We have an interesting situation where as things are changing, we are getting a lot of new terms that some of us might not be familiar with. One of them is the global warming potential, GWP, expressed as a carbon dioxide equivalent. And that's because carbon dioxide is a greenhouse gas. It has different atoms, carbon and oxygen bonded together, and therefore it can store heat effectively. Most of the air around us is made of oxygen, about 21%, and nitrogen, about 78%. And those are two N's or two O's. That doesn't store heat. But the other gases that are in this room, which are probably in order of size, water, which is H and O, carbon dioxide, which is C and O, and methane and various other hydrocarbons, which are C and H. All of those will absorb light, incident radiation, and turn it into heat. So when we have a global warming potential that's so-called greenhouse gases that heat the atmosphere up. And we know this is the case. We know that if it wasn't for greenhouse gases in the air, particularly water, that the Earth would be considerably cooler than it is today. And that's well known. It's been well established long before the politicians got involved. But now we're going to determine the quality of our concrete not based on how well it sets, how well it sets, and or how much it costs. We're also going to have another measure of quality, which is its global warming potential. And so we are going to see a lot of work done in the subsequent presentations. But we should be aware that these are now being legislated. This isn't something that we're choosing to do because we think it's a great idea. This is something that the government has decided that you concrete people are ruining the world, and as a consequence, it's absolutely necessary for you to be controlled. And so there are state requirements, there are federal requirements. They are going to be based on global warming potential, and they are scheduled to go down with time. In fact, that is exactly what is promised. So let's take a look at what some of these things look like. In California, I put California in there on purpose. California, that's right, the home of the gold rush. They have no requirements for concrete. And the reason they have no requirement for concrete is because they're concerned that no mill in the United States will then be able to provide cement because they'll be able to get much lower cement, GWP,
from overseas, because I'm sure that's what really happens. But that having been said, they do have a requirement for steel reinforcement. And steel reinforcement, you are allowed to emit 1.06 metric tons of CO2 global warming equivalent per ton of reinforcing steel. And I put that in on purpose because it's a relatively large number as compared with, say, New York State. New York State has requirements they have published. They're optional now. They become mandatory in January of 2025, and they will be reduced, that's in the legislation, by January of 2027. And so they have listed the compressive strengths, including the very accurate 4,999 PSI, which we are all laughing at now, but since the difference between 4,999 and 5,000 is what is that, 24 kilograms per cubic meter? You can be sure that there will be a lot of 4,999 PSI specified. And you can see that it's going to happen, right? Because we're all going to try to solve our problem. And so you can see we're allowed to emit for low-strength concrete as much as 275 kilograms per cubic meter. Now, there's 1.6 pounds in a kilogram, so in round numbers, let's do 2,500. 302 is about 480 pounds, and a cubic meter of concrete weighs about 2,600 kilograms, so what is that, 2,600 plus 12, it's about 3,000 pounds. So you're looking at about 480 pounds in 3,000 as opposed to the 1.06 or 1,060 you're allowed per ton of reinforcing steel. And so we are having relatively low numbers. But it's getting better. This, by the way, doesn't tell us what the basis is. However, the U.S. General Services Administration, as part of the Inflation Reduction Act, has low embodied carbon concrete requirements. And here you can see we are less than 2499 again, and then 3,000, 4,000, and then greater than 7,200. And we have three numbers there. We have the top 20% limit, the top 40% limit, and the better than average limit. And these limits, all of these numbers come from the NRMCA survey for the East Coast, the Northeast region, and further, it allows you an additional 30% for high early strength. And then that is required to have a technical justification, but no description of what that is. So these are representations of the owner that are put together, and very frequently we are required to construct what the owner says that they want. Now, the beauty is in the eye of the beholder. This is what a chair that will not let you fall asleep in it while you're reading. One of the difficulties that we have is that it's very easy to concentrate on one aspect of the design and not others. For example, a problem occurs where you are packing tennis balls in tubes. Anyone play tennis ever at any time, right? So you can buy a sleeve of tennis balls, right? How many tennis balls do you get in a sleeve? Typically get 3. So an engineering problem could be, how could we put more tennis balls into a sleeve without increasing the size of the sleeve? And it's relatively simple to solve. As you can see on the right-hand side, I have solved this engineering problem, and I have put 5 tennis balls into the sleeve where you could only put in 3. Now, the tennis balls are no longer useful. However, I wish to point out that I did meet the requirement of the assignment, which is I have more tennis balls. And this is part of the issue that we're encountering, is we're going to go forward, and we are having, we have changed most of the Portland cement in most of North America contains some amount of finely divided limestone. And we are seeing some problems that are occurring for the users of that material, not in terms of strength, but in terms of setting and in terms of strength, in terms of finishability, and sometimes in terms of strength gain if the temperature isn't the balmy 72 degrees that is presented in all engineering textbooks. So when we have this particular problem, as we ramp down our global warming potential requirements, we're going to see other solutions. And in fact, in the news, there's a couple today of entities that have been given funding from the Department of Energy to proceed forward with their plants, and they are going to make ASTM C1157 cements. And those ASTM C1157 cements that they're making don't have any ground clinker in them at all. In fact, many of them are carbon negative, which means that, depending on who's doing the accounting, they have no global warming potential. And that's fine. We've been building for a long time. Long before we had Portland cement, we could make Egyptian concrete. We could mix mud with straw and some lime mortar, maybe some burnt gypsum, put it all together. It'll be non-hydraulic. And those of you that have been paying attention to geopolymers for a while will know that, in general, there is a very well-established and multi-investigation now evidence that the pyramids, you don't need to worry about how did they cut the stones and how did they drag them across the desert, because they cast them all in place. This is a set of recipes courtesy of Dr. Davidovitz, and how you make pyramids using materials that were known to the Egyptians. Natron is a source of sodium, and halite is rock salt. The Romans made concrete without any Portland cement clinker, so they were fine as well. They rammed their materials in place. We even talk about pozzolans, a word that they were familiar with. And if we read Vitruvius's book of architecture, his 10 books of architecture, one of them talks about the amazing sand on the slopes of Mount Vesuvius, when mixed with lime, will harden underwater. And we may make fun of the poor Romans, but this is a piece of Roman concrete taken from the port of Trajan in Naples. And it looks an awful, it's gap graded, which means that they had the tarantula curve, but also that it has been rammed into place, and it looks for all the world like modern concrete. And I've been making concretes with very little global warming potential for a long time. This is a piece of concrete that Dick Staley, the late Dick Staley, and I worked on many, many years ago. You can see all the recycled aggregate in there, causing all kinds of problems. These concretes have almost no non-recycled material in them. They still have global warming potential because you still have to haul the material to the plant and then haul the material from the plant to the site. But these have been used in practice. This is a core taken from a drill shaft about 60 feet deep at for a bridge under construction in Minnesota. And it had some very interesting properties, one of which was it had almost no cementitious material in it, let alone Portland cement. Intended to be 4,000 psi. Compressive strength in the laboratory cured was 8,500 psi. 10,000 psi by in situ cores. And so it was designed to have a lot of other engineering properties. So rather than just meeting the strength requirement, a la the cut up tennis balls, we had to meet a temperature requirement and a durability requirement. And so I thought it would be interesting to look at some more typical concrete mixtures along with these very low green global warming potential mixtures and see how they're doing. So I found there's a source, a Circular Ecology, has an online calculator. So it is supposed to calculate what the global warming potential CO2 equivalent is of your concrete mixture if you put a bunch of data in. I had it hauled 15 miles. It's the same slump, similar strengths in the designed to be 4,000 psi air and train concrete, and 600 pounds of material per yard. And this is what I came up with. The first mixture is 15% Portland cement by mass. It's wonderful stuff. It does not emit very much CO2 emissions, and if you cure it properly, then you're going to be just fine. The second mixture is a straight cement mixture, perhaps for a slab on grade, and the third one has a 25% slag replacement. The global warming potential is calculated in kilograms per cubic meter below, and you can see that I can make really low. 113, that's super low. That meets everybody's requirements. So using straight cement, which many floor finishes require, does not meet those requirements. And further, the 25% slag does, but I picked 25% on purpose. At about 25% slag is where the material starts to behave differently under a trowel. And that has to do with if you've ever taken a slag, granulated slag nodule and placed water on the surface, you'll see that it beads up. It has a Washburn angle in excess of 180 degrees, just like the same way if you wax your car. Whereas Portland cement, it will wet out. And as the slag content increases, the resistance to finishing properly increases. It changes the feel under the trowel. And the difficulty that we have as a, quote, learned profession, unquote, of engineering is we can understand that. The trades who have learned in a different way, much smarter than I am, I can't finish a slab. You should see, I tried once. Once was enough. That what the concrete looks like is different from what it's going to behave like if you change the cementitious binder enough. This becomes a problem, and guess where this is not written? It's not in the specifications. That first mixture will be 10,000 psi at 20 days. However, it's purposely put up faintly so you don't have to read it. It requires specialized curing. If you cure it where it is not able to self-stoke, to self-anneal, to heat itself up to about 130 or 140 degrees Fahrenheit, it is not going to behave very nicely for the first, 7 to 10 days. So if you're okay with curing the day or finishing tomorrow and maybe cutting the joints the day after tomorrow in your floor, that's no problem. We all know that the owner schedule says, I'm using low global warming potential concrete, so you take whatever time is required to get that slab in place. You don't fret, don't worry yourself. It's the GC that says we got to get going, right? And so part of our problem has to do with a similar problem of development of technology that occurred in the 1950s. And many of you may have never heard of Admiral Rickover, the father of the nuclear navy, but he gave a paper once on the difference between paper reactors and real reactors. And he stated that an academic reactor or a paper reactor is almost always simple, it's small, it's cheap, it's light, it can be built quickly using off-the-shelf components. That reactor is always in the study phase. It's not been built. And now we have a lot of concrete that people have been talking about. And in fact, I am the named inventor on one material that has no carbon, no clinker in it at all, and is a wonderful material. It's carbon neutral. However, it's in real production. And what we found, just like Admiral Rickover, is that real reactors, real concrete is being built now, is behind schedule, requires an immense amount of development for apparently trivial things. It's expensive. It takes a long time to build. It's large, it's heavy, it's complicated. And this is where we're heading, because as we develop new materials that don't have any clinker in them at all, we're going to look back wistfully for the days when we had type 1L cement. Many of our technologies that we're talking about as serious people, and that you can learn about down in the exhibit hall here, are unproven at scale. We don't know what's going to happen with those materials when we start trying to make them at 200 cubic yards an hour and try to put them down with our conventional plants, conventional equipment, and conventional people. And the other, and this is clear if you read ITG 10, which was published some time ago. In fact, it was published more than 6 years ago because the first chairman of the committee that it spawned her term is up. There are latent defects that we don't know about. If we were in this presentation and it was 1924, we wouldn't know about alkali silica reaction. It wasn't really well known at that time. Cement set very slowly, so we didn't need to worry too much about rapid strength gain or rapid curling. And so the takeaway from this presentation is that low global warming potential concrete is available right now, and it can be made to be as close to zero or negative as you want, but it's not the same. And until we can change our documents, our construction methods, our codes, and our specifications to reflect the fact that it's not the same, and that we push the training both in two directions. It has to go forward for the structural engineers as well as forward for the contractors. We are going to have problems. So thank you so much for the time. And if there's any time for questions, if not, you can read about strain.
If anyone has